All right. Now we're cooking with bacon grease. Here we go. Okay, so magnification. Magnification is a misrepresentation of size of an object. So here we're not talking about changing the shape of something. You notice that hand that I showed you was unsharp, right? But ignoring the fact that it was unsharp compared to the first one, that hand was larger on screen than the first one. It was a physically larger looking hand. That was the same hand though. I used the same hand for both images, right? So what changed here? Okay. Magnification deals with the distance from the surface of the object to the image receptor and the distance from the source of radiation to the surface of the object. Okay. As you bring an object away from an image receptor, now you can show this really simply with just a flashlight, right? As you take some source of radiation, my flashlight, and move some object away from where the shadow is being cast, the image receptor, whiteboard's image receptor, you notice the shadow of my hand gets larger. On top of like the recognizability of my hand changing too, the shadow gets larger. So we want to know, how can we figure out how much larger something is, right? So one key note is, no matter what your OID is, if you purport that your OID is 0, it's never 0, right? Even a finger has some thickness to it, right? So it's never exactly 0. So we can predict and calculate magnification. This will happen on one of the X-ray labs that we'll do, but we'll be able to have a formula for it now. Simply put, if you know the source to image distance and the source to object distance, you can tell me relative how much larger this next body part is, or the body part is that you're imaging, okay? So let's make something up. Let's say that one of the metacarpals in that hand that we x-rayed was 3 inches long, okay? So let's erase some stuff on the board here. So metacarpal of hand equals, no, not 3 inches. Let's use centimeters. So how do I convert from 3 inches into centimeters? One more time? 0.54. Sorry. Multiply by 2.54. 3 times 2.54 is 7.6 and change. Ignore the change. Okay? 7.6 centimeters long. That's how long one of the metacarpals in that hand was, assuming, okay? In centimeters. I need to know 2 things, right? SID and SOD. Let's use the first image of the hand. Okay, the first one that we took. So you're just holding in your mind the first image of the hand that we took with these factors. Magnification equals SID divided by SOD. And this is not going to tell you how big the thing is. This is going to tell you how much bigger it is on the image than it is in real life. Okay? It's sort of a 2-step process here. SID for image number 1 was 100 centimeters. SOD for image number 1 is 96 centimeters. The body part was on the table, and the tube was far away from it. So source to object distance is big. The other key thing is it's always going to be a number bigger than 1. So we take 100, divide by 96. This is your magnification factor, okay? This is telling you the object that you took the image of is going to be 1.04 times the size that it is in the real world, okay? Said it another way, that object is going to be 4% larger on the X-ray. So it'll be 4% larger on X-ray. You guys following where I'm getting the 4% from? This part of it. So this is saying the object is as big as it is in real life, plus 4%. Okay? Let's do the other one. Let's do the smaller hand, and then I will give you the numbers here. Or the larger hand, sorry. So we're going to do this one now, okay? The larger hand, okay, had an SID of 76 centimeters and an SOD of 40 centimeters. So we need to plug that in. You guys feel free to do that. 76 divided by 40, 76 divided by 40. What's that telling me?
90%.
It's going to be as big as it was, plus 90%, right? It's going to be almost twice the size, okay? Because the ratio of the source to image distance to the source to object distance is almost 2 to 1. Okay? Almost 2 to 1. So the object is almost twice as big as it is in real life. If the SID were 80, then this would be exactly 2 to 1. The object would be exactly twice the size that it is in the real world. Okay? So let's put this to work. The size of the hand, the metacarpal in real life, this is real life. In the real world, real life metacarpal of the hand is 7.6 centimeters. On this first radiograph, it would be 7.6 times 1.04. We don't get scared of things like that because we've got phones, calculators, times 1.04. That hand is now going to be on the radiograph 7.9 centimeters. How much bigger did that hand get? Or did the metacarpal of the hand get? It got 0.3 centimeters bigger. 4% bigger, 0.3 centimeters bigger. That's what it came out to. So the radiograph gave me a hand, or at least the metacarpal of the hand, that was a little bit larger. Okay? Let's look at this next one. 7.6 centimeters in real life, multiplied by their magnification factor. We're going to run that through 7.6 times 1.9 equals 14.4 centimeters. The hand in the second image, the metacarpal of that hand, was 14.4 centimeters. A lot bigger, right? Why was the second hand's metacarpal so much larger? What did I do in this second image that changed that so much? I brought the source of radiation closer. So we had a small source to object distance. And what else did I say I did? The object to image distance, right? It was elevated, right? This image 2 over there is so much bigger, so magnified, because I had a large OID and a small SOD. Okay? Image number 1 was not that magnified. It only got 1/3 of a centimeter bigger, right? 3 millimeters larger. Okay? Yeah.
I lost track of that. How did you get that 7.6?
So we just said the metacarpal was 3 inches long, right? That's the real world measurement. You went to somebody's body part and you took a ruler and you measured the length of that body part. Okay.
Yeah, I was lost because you're like
Gotcha. Sorry, I was putting my belly in the way. So we measure it, right? We take the real world size by measurement on a ruler, and then we can say, given the things that we know, the things that we can measure, how much larger is that X-ray going to be? Okay. No matter what you do, or let me ask it a different way, is there anything you can do to have no magnification? Like, what could you do to have no magnification?
You can machine the numbers even.
You could maximize source to image distance, right? You can make that bigger, okay? You can maximize that and minimize that, right? Sorry, if you can maximize that and maximize that, right? You can make the magnification smaller, but there's nothing I can do to make my object to image distance 0, right? The only way to have no magnification is if your source to image distance equaled your source to object distance, and that can't happen. Why can't that happen? Why can't your SID and SOD be the same? because body parts always have some thickness to them, right? There is never a case where the only time your SOD and SID can be the same is if your OID was 0. Because how do you figure out SOD? So if you can see down here, right? SID, right, minus OID equals SOD, right? So if your OID was 0, then it would just be SID minus 0. So SID would equal SOD. You can't have an OID that is 0. Because you can't have a 0 OID, you will always have a source to object distance that's smaller than the source to image distance. That means you will always have a magnification factor that's bigger than 1. Okay? Make sense? If your SID was 100 and your source to object distance was also 100, that'd be a magnification factor of 1. 100 over 100 is 1, right? Cross out the zeros, 1 over 1 is 1. That'd mean the body part would look as big as it is in the X-ray as it is in real life, but that would mean that your body part could not have a thickness. We always have a thickness, everything, okay? So you can never not magnify something. All you can do is minimize the magnification. That's the point of showing you this, right? Not so you can play with the formula. You can, and you can do this yourself. But just doing 2 of these can show you that you can never make the magnification 0. You can just have less of it, okay? Like I did in this one, okay? This is pretty realistic. An object is 3 millimeters larger on the X-ray than it is in the real world. You're not going to have on screen, it's not going to make a difference to you that the object is 3 millimeters larger, right? The image is sharp. That's what you're caring about, okay? And then there's that relationship, right? Magnification and sharpness go together, right? Things get magnified when you have a large OID and a small SID, right? Things also get unsharp in those circumstances too. So we want to minimize magnification, maximize spatial resolution detail, and those 2 things go sort of hand in hand with each other. Anybody have any questions here? It's a good time to ask those questions. Made sense in my head. I don't know if it makes sense in everyone else's head, so that's why you have to ask the questions. All right, moving on.